Assignment number 0. How was that?
I have to ask a question about it.
Yeah.
Are all those different, just the different areas, are those something like to test general knowledge of those areas, or are those kind of the bulk of what we need to be applying in those? Like
It is kind of like very general, like you'll need to learn more,
Okay.
but that is kind of like the minimal that I require. Yes.
For assignment 0, there were some questions where there was very little work to show. Like the first calculus problem was like a very basic derivative. If we just put the derivative, are we fine there?
Yeah. The goal of assignment 0 is to just let you know, like, these are the minimum background I'm looking for. We're not really testing you there. It's more like a filter. Yes.
The last part where you're pulling the data set,
Yes.
the TAR-DC, unless there was like some information I didn't see to extract, I extracted the data set, like the training set, the test set, and then that like informational thing. It had in the informational all the field names and then the potential variables you'd see, but it was just listed in terms of like bytecode that you had turned into strings. Are all of these gonna have like, or not like lack a list of like field names that you can map to the columns? Because it was all just like 0, 40, like till 41 in the column names, and there was no, I couldn't figure out a clean way of mapping field names to those columns.
But you have a list of attributes in the like description, right?
Yeah, but it just felt kind of like really too manual, like to have to go and do it by hand. They're like, are all these data sets going to have to be done manually, or will there be like a field list that you can map?
Well, it depends on the data set that is available. If this data set, like, first of all, if there was no direct like mapping, what you should assume is the list that you have in the attribute names should map to like sequential to 0, 1 and all that.
Some of them were a little out of order in how they were listed in the informational versus the columns and the thing. That's why it felt a little like you might be mapping the wrong thing.
Okay, so you are saying the actual data file, and there was no direct mapping between the column 0 to what it means in the actual
Yeah, 'cause
column.
the informational file you could turn into a string in Python, and it did have a section where it said like these are the fields colon like potential variable attribute like output stuff that you have, but how they were listed sequentially didn't necessarily map to the order in the column.
Okay, let me take a look into this, because this is something that we didn't realize, or like when we actually gave you the assignment. Let me have my TA to look into this. Like, if there is, the whole point of this assignment was, forget about the accuracy of the numbers you computed. Can you load a data set, a big enough data set using Python? That's what we are looking for in this assignment. We just want you to be able, we just want a minimum background who can write a code on Python, load a data set, do some addition, average kind of basic things. That's all that was about. Okay, if you had the wrong column, wrong name, it doesn't matter. It doesn't matter. All right. Okay, but we will look into this, and I'll get back to you. Any other questions? Yeah.
Do you ever release answers for your assignments once they're like past the due date?
The answers?
Yeah.
Yeah, so we have classes where we are going to discuss the solutions. There will be a dedicated session. If you are particularly interested in an answer right now, the only way to do that is to go to office hours of the TA and discuss with them. But we'll have a separate class where we will actually go over the assignments, what should be the solution, and we feel the right time to do that is before the midterm comes, so that your memory is fresh. So the first 4 assignments that we are going to start from today will be covered in your midterm 1. So we'll be having that discussion session of the 4 assignments together in a class. Okay? All right. Any other questions? Yes.
When do you introduce the
Turn project. Are we supposed to select today? The topic?
topic selection is due Tuesday night.
Tuesday, next Tuesday.
Next
Okay, then I'm going to do that on the next Tuesday class. Okay? All right. Yes.
How do we do teams for that?
What?
Do you assign the groups for that, or do we pick our groups?
That's what we are going to discuss. Or maybe after today's class, if there is time, which I expect there will be some time because I don't have much content to cover, and then we can go over that, okay? I'll go over project either in this class or the next class. Are we good? All right. So, in the last class, we were talking a lot about information gain, the best attribute to pick, and the idea of entropy, right? So, what was entropy? What does it mean? Level of uncertainty, okay? And what is information gain? Reduction in uncertainty, right? So entropy is the uncertainty, gain is the reduction in entropy. What is a random variable? It's a function, but can it be any function? What kind of function is it? Target function. Okay, yeah, by definition, random variable is not a target function, but in our case, the target function, we are assuming that to be a random variable. And why are we doing that? Why is that random? Yeah.
So we don't know if he's going to play tennis or not?
Yeah, because it's random. We don't know. If I tell you, without any information, you don't have anything, no data set, no example, nothing. Is Alex going to play tennis? What would be your response like? Don't know. Or what is the probability you are going to put? Play and versus not play.
0.5, 0.5.
Right? I mean, equal, if you assume uniform probability, that will maybe 50% of the chance he is going to play, maybe 50% of the chance he is not going to play. Right? That's the most uncertain case. You don't know. But if I just tell you the last column only for 14 days, nothing else, you have more information, right? Now you know how many times Alex plays? 9 days, right? Or is it the other way? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. Yes is 9 times and no is 5 times. Now what is your probability if I just tell you this? That column.
Probability of play is more.
Yeah, it's more likely that Alex is going to play. You have more information. And you have less uncertainty. You have reduced uncertainty from 50-50 to 9 by 14, 5 by 14, right? You are more certain about something. Now if I keep giving you more information, your uncertainty drops. Remember? Adding more information cannot increase your uncertainty. It can only remain the same. For example, it doesn't help. For example, if I tell you like, Matthew plays tennis on this day, that doesn't really help what Alex is going to do, unless I establish some other relation. Then the uncertainty will remain the same for Alex. Or if there is a connection between Matthew and Alex, it will go down. It will never go up. Okay? All right. So far we know what we are talking about. We know what the idea of entropy is and what was the gain, right? So we defined gain, and gain is basically information gain. So we assumed, so coming back to the question, why is play tennis a random variable? Because initially we don't know. There is randomness, and eventually there may still be randomness, depending on your data and evidence. What you are trying to do, so there is always uncertainty in real life, right? You can never guarantee like something is going to happen with 100%. So every event can be assumed as long as they have multiple possibilities, can be assumed to be a random variable, even though you have sufficient information. But you never have enough. Maybe you don't have all the variables that define them, right? And initially you don't know anything. So your outcome is random. And that's why the output that we are trying to learn is probabilistic in nature. Sometimes we can have a very high confidence. We can get close to 100%. That's great. But really reaching 100% is probably not going to happen with real life data. That's why we assume this is a random variable, but we want to decrease the uncertainty associated with that variable, because if we had known what is the outcome, then there is nothing to learn. The learning is basically about reducing your uncertainty. That is all machine learning is about. Based on the data, you reduce your uncertainty of making a decision. Okay? All right. So initially you have some uncertainty. Let's say this is our target variable, right? And this is the uncertainty without any further information. Just about looking at this outcome variable versus how much we reduce that uncertainty given that we know about some attribute A. If I tell you Matthew plays tennis, and if I say Matthew and Alex are buddies and they always play together, then that variable A, if that is Matthew playing, then this will mean what? Alex is also going to play, right? The uncertainty will be almost zero. And you will have the maximum gain by knowing that Matthew and Alex plays together, and maybe Matthew is playing today, right? Okay, but then this variable might have many possible outcomes. That is also another variable which may be random, right? Matthew can either play or not play. If Matthew doesn't play, then what happens to Alex? Does he play or not? Or if Matthew does not play, what happens to Alex? So you need to consider all the possibilities of A in order to quantify the uncertainty of X. That is the conditional probability kind of idea. It's the same with entropy. It's a conditional entropy. It is conditioned on another variable, so you need to consider all the possible cases for variable A. Is that clear? Now, if you consider all the possibilities, how do you combine? Because for each possibility there will be an entropy, right? So you basically combine all the possible cases with a weighted average. And that's why the equation that you see here is like this. So we are basically replacing this thing with a weighted sum, the expected entropy for all the values of A, entropy of X, given that A is equals to A, right? Sorry, V. We have V here, all the values. And we basically are saying this set is XV. That is your SV here. I just replace S with X. But in that case, because you are summing over, you need to do a weighted average as well. Because how many, maybe X has 3 different values. X, V1, V2, and V3, right? So you need to take the weighted average of x v divided by entire x, the size of your data. Because you are essentially partitioning between the three possible values. In how many cases, so this basically means in how many cases you see the value of v for a. Now now remember, this partition is based on a. It is based on a. It is not, we are not partitioning with respect to x here, because this is given a, and a can have three different values. So for this value, you are looking at this target random variable. What happens to this x when a is v1? What happens to x when a is v2? What happened to the same x when a is v3? And how many times a is equal to v3? That is what this size is. Because you are just putting a weighted average to the size of each value, I mean to the dimension cardinality of each value of a. All right? So let's go through an example. And actually, let's have our data ready so that I don't have to look every time. So D1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So first to no and then the 3. So no, no, yes, 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 and then no, yes, no, yes. And then no and no, here and here, everything else is yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 5. Yeah. So this is our data set, right? That is given. Now, first of all, if I don't tell you anything, whether Alex is going to play tennis or not, what is your probability? 0.5, right? Whether going to play or not, uniform probability assumption. What is the entropy in that case? 1. So our uncertainty is initially 1, maximal, right? Okay, now I look at this data without looking at any other variable, just the target variable. And what is your uncertainty right now? So we basically compute the entropy of play tennis, right? Initially, that was 1, without knowing anything. But if I now look at this data, my entropy is going to be 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. Clear? Any question on this? And what is this value? This is equal to 0.94, right? I mean, if you compute that, that's what it's going to be. So we have came down from 1 to 0.94. That's good. We have made some progress. But is that good enough? What is our goal? Make it 0, right? It may not be always possible, but we want to make it 0. Right? Okay. Good. So now, because we cannot make a decision just looking at the target variable, there is still uncertainty. We need to do more. What we are going to do? Now we are going to look at additional signals. So this is our first uncertainty. The second one is 0.94. Now we have to actually build a decision model. That is our decision tree, right? We need to, so to build a decision tree, we first need to decide split on a particular attribute. But the question was which attribute to split on, and we said like the best attribute. And what is our definition of best? The one that gives you the maximum information gain. And the definition of information gain is the reduction in entropy. So we have to compute the information gain for all the variables we have and then pick the best one. And why this is a greedy algorithm? Because we are just looking at the correlation between or the gain with respect to a particular variable and the final variable. We are not looking at the whole story. We are just considering what is my best option right now. And that's fine. That works pretty good in real life. And actually in my group, we actually won a national challenge last year by using decision tree, believe it or not, in this age of neural networks and all that. Okay? Well, we didn't actually have just a single tree. We had a collection of trees, which is called a random forest. Okay? And yeah, we won $50K. That's the best part, right? So, and the Alex you saw in the picture, he actually led that like competition. So he also got portion of the money. All right. Okay, so now the question is which attribute to split on, right? And you see two examples here. Like we need to consider all four of them, but let's consider if we had chosen humidity, what would happen? And we want to compute what? The entropy reduction if we choose humidity, the information gain of humidity, right? So you need to compute what is entropy of, let's call the play tennis X minus, sorry. Let me just play tennis, let me call it PT, minus entropy of PT given humidity. Right? This is what we need to compute. So what is PT? H of PT, what is that? 0.94, right? We have already computed this. So all we need to compute is, what is this? And how many options do you have for humidity from the table? How many? 2. Either high or normal. These are the two options you have. So if it is high, you have something. If it is normal, you have something, right? Okay. If humidity is high, what are those examples? We need to now partition this data set based on humidity. So we need to look back to that 14 rows, right? And you need to see high, 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 and high. So D1 to D4, it belongs here. D1, 2, 3, 4. Normal, next 3. So 5, 6, 7. high, and then 3 normal. 8, 9, 10, 11. High, normal, high. 12, 14, 13. Right? I mean, these are the cases where your humidity is high. And these are the cases where your humidity is normal. Right? And based on that, you get 2 different partitions. And you'll have 2 different entropies here in these partitions. Right? Okay, how do I compute the entropy of this part? Just consider now this is your data set. Because you have already branched down. Yes?
Count how many yes or no's there are for tennis, and then you get the fraction, you plug it into the log entropy thing.
Yeah. How many of you understood this? How many of you are still confused what he said? Good. So we basically want to look at how many of them are positive labels and negative labels. And label is our what? Which variable? What is our target? Play tennis, right? So D1, play tennis is negative. It's negative. D2 is negative. D3 is positive. D4, positive. D8, negative. D12, positive. And D13, oh, there is no D13. D14 is negative, right? So how many negative? 1, 2, 3, 4. So 3 negative and 4 positive, right? Did I make any mistake? It's the other way around. So I made some mistake. What? 1, 2, 3, right? Yeah, I wrote it the wrong way. Right, 3 positive. 1, 2, 3, 4. Yes, 4 negative, right? Although it doesn't change your uncertainty, but yeah, this is the right way. And then what happens here? D5, positive. D6, negative. D7, positive. D9, positive. D10, positive. 11, positive. 13, positive. So 1 negative. 6 positive, right? So you see the point here, like when the humidity is normal, there is a high chance Alex is going to play. But when humidity is high, not so much. So how do I combine? So humidity helps to some degree, right? Because if humidity is normal, there is a high chance Alex is going to play. It gives you some information. It's not like entirely useless. This portion is kind of useless, right? If it is high, you don't know. But still, for this one, you have some information. So we need to combine the uncertainty of both cases and have an average, like expected entropy and reduction in entropy. We need to compute for humidity. How? So this one is what is the entropy for this partition? Tell me the formula. Minus 3 by 4, right? You take a log. 3 by 4. Minus, is that a 4?
3 by 7.
Yeah. Right. 3 by 7. Minus 4 by 7. Log 2, 4 by 7. What is that value? That should come to something like 0.985. Okay? What happens here? Minus 1 by 6 log 2 base 1 by 6 minus, no, that's 7, right? 6 by 7 log 6 by 7, right? This is 7. And that value is something like 0.592. You see? There is less uncertainty, and you see the number going down. Right? So, but this is the uncertainty when humidity is normal. This is the uncertainty when humidity is high. But if I don't know it, like what is the humidity, then what should be my expected uncertainty if I know humidity? Just assume that I know what the humidity value is. If I assume that somebody tells me, but I don't know it yet, I'm going to know. What should be my expectation of uncertainty? You just need to take a weighted average of these two. And how do you weight? You weight by how many cases you have high and how many cases you have normal. Because that is the likelihood you are going to see normal, then times the uncertainty. Plus number of cases here, the proportion times the uncertainty. So it's basically you have 7 here, 7 there. What you do is you have 7 by 14 times plus 7 by 14 times the other uncertainty. So this one goes here, 0.98, and that is 0.59. Right? This is the expected information entropy of clay tennis if you know what humidity is. And what is the information gain? You just, originally it was this, right? Before we knew humidity. So you subtract from that this value. And that value is 0.15. So not much gain. There is some gain, 0.15. Not much. Any question? Now you can do the same thing for wind, right? You can do the same thing for outlook, and you can do the same thing for temperature. And once you do that, then immediately based on your calculation, it will be outlook that gives you the most information. So then you basically forget all of this. You just forget all of this. Now, so far we're imagining a tree, but now you have a real tree by putting in outlook here, because that gives you the maximum information gain. And outlook has 3 values, right? Sunny, overcast, and rain. Sunny, overcast, and rain. And based on that, now you do real partitioning, right? You need to partition to move forward. So, sunny, 1, 2. Sunny, D8, D9. And 11. Okay, good. Overcast, 3. 7, 12, 13. Thank you. Rain, 4, 5, 6, 10, 14. Okay. Right? 5, 5, and 4. And we need to compute the entropy of these partitions, right? To decide whether we need to move forward or not. For example, if outlook is overcast, what are the labels you have? D3, positive. D7, positive. 12, positive, 13 positive. Do we have a solid decision here? Are we certain? Yes. So, yes. And this part is done. You don't need to move forward. But what happens in Sunny? D1, negative. D2, negative. D8, negative. D9, positive. 11, positive. So, 3 negative, 2 positive. High uncertainty. Not good. Need to move forward. The same thing here. Rain, D4, positive. 5 positive. 6 negative. 10 positive. 14 negative. Similar kind of 3 positive, 2 negative. The same uncertainty in these two nodes. And then, now this becomes our data set. And we need to do the feature selection again. Which attribute to select? We just don't consider Outlook anymore because we have already considered it. Right? And you keep doing until you hit a decision, like a 100% solid decision, a certain decision. Questions so far?
So if you know you can exclude several of the days by that overcast, will you not use those in the calculations for other criteria?
For example?
Like you can exclude those if next you're going to calculate for temperature, you don't have to consider those if you already know you can have a decision based on the overcast.
Right. If it is overcast, we are not going to do anything else. But this depends on what. So look, there are two different things, right? One is your knowledge that you are trying to build, and the other one is your decision that you are going to take. If you know for a particular day it's overcast, you don't need to go through the other like branches of the tree. But for your knowledge to be complete, you also need to consider what happens if it is sunny. So the knowledge base has to have everything, yes.
Okay, I understood that. I just mean when you're calculating the entropy for the other criteria, can you go ahead and exclude the ones that you know you have a dead end on you know the decision for those already. So.
Right. That's why I'm saying. So once you go down this route, you never look at Outlook again in none of these branches because you have already considered the Outlook variable. So here, your choice becomes between only the other three variables: temperature, humidity, and wind.
But the actual elements, the actual days in those other attributes, are you going to consider day 12 with that sunny? I don't mean using the tree. I mean when you're building the tree.
Day 12 with that sunny. No, this is your data set now.
Oh, right.
All you do here, it starts from here. You are not looking at any of them anymore. You have already split your data. You have already considered those cases, and you are going to go that route once you process, right? Building the tree. Yes?
So then what gets put in the next box, you just recalculate all the entities and figure out what's the next highest
Yeah.
to gain?
Yeah. And keep doing that until you have a leaf node, like a decision, so 100%. Your entropy is 0. Recursion, right? Yes.
What if the entropy never ends up being 0? Do you just keep
Good
going
question.
run out?
Good question. The question is, what if the entropy never runs, like becomes 0? Is that possible? When is that possible? Yes. Exactly. Like if you have two exact similar rows, but one has a yes and one has a no, you can never reach that. At that point, that's it. You cannot resolve that case. You have conflicting examples. Right? In that case, you just need to stop because you don't have any more examples. You have just two. If you partition them, there is nothing to do. I mean, this is the only two examples you have, and you have considered all the possible variables. And still you don't have, because there is no other variable to iterate over. You stop there. Right? Yes?
So in that case, so then when you have a mix, do you just do like a combo, like do like two yeses and one no, or do you just do like a
That depends on you. Whatever you like. That depends on the domain. Is saying yes by default is a better choice or saying no? That's on you. It could go either way, 50-50. All right. Question? Good. So, you see, this is the example that happens then. Like, the question was, am I going to look at the other variables? No. The point is, if you have a sunny value, your entire data set has reduced to this 1, 2, 3, 4, 5 points. That is now your entire data set. And based on that, you are doing all the calculation. Look, this initial probability is no longer 0.94, it's 0.97. Because now, the initial probability here is 3 negative and 2 positive, right? That's what gives you your 0.97. It's no longer the initial 9 positive and 5 negative. No, that is not the case. This is the case here. So if you do that, this is your final tree, which we have already shown in the beginning. Right? Now let's talk about some of the properties of this algorithm that we just learned. This is a greedy algorithm, I already told you, right? We are choosing one attribute at a time. It doesn't guarantee that it's the best tree, but it at least guarantees it is one of the good trees, right? It may not be we wanted a smallest tree. It may not be the exact optimal smallest tree, but it guarantees that it is one of the good smallest trees. Just because of the greedy algorithm nature we considered. So that's what the good means, like acceptable. This is an acceptable version. This kind of do our job and have this heuristic of having using minimum number of attributes because we are choosing the best attribute at each point. And then this is essentially one kind of search we are doing, right? Think about all the possible trees you could create and searching through that, which one is my best one? And we just use some heuristic to do that. And we came up with a pretty efficient way of searching through this massive space of decision trees, and we have something reasonable, as long as we have something reasonably usable. And as I told you many times in research papers, and although I take it back, in recent days, people think decision tree is not cool. Random forest, we need neural networks, right? No, believe me, not always you need complicated deep learning neural networks. This can still do magic for you in a lot of domains. Okay? All right. So in that sense, it also goes with Occam's razor, which basically says, consider the simplest hypothesis that explains your data. We are considering the simplest, smallest kind of one small kind of tree that explains my data. Yes, things can go wrong forever if your training data is such that there are conflicting examples, but that's just bad data. I mean, that basically means it's a random process. It's actually truly random. The assumption you made initially that the target variable is random is true. And you cannot do anything about it. No neural network is going to solve that. Okay? All right. So it tends to have the right bias. That basically means short decision trees, but it can still overfit. Now, the question is, what is overfitting? And we talked a little bit about overfitting in the first class, but let's think more about when can it overfit? What does it even mean to overfit? And how does it correlate with tree? Yes, go ahead.
Is it just that it's customizing kind of to the data set that you're training on?
Very good. Yes.
In the output variability you have for data, there's going to be inherent lack of information variability in the model we're trying to not only fit the systematic information, but also that random.
The randomness in the data. Okay. Yeah. Yeah, good. So tell me, what is the most overfit model here? If we think about overfitting, like I'm trying to capture everything in the training data, like I'm trying to capture too much. What is the most overfitted data, like model?
It just recreates the data set perfectly.
Exactly. Just memorize the entire thing. And in the first class, we said like memorizing the entire table is not a good idea, right? But that is still you can still have that a tree from just by memorizing every possible instance. Go through the depth for 4 attributes every time. You can just memorize the entire tree. Entire data set. That is just too much. It doesn't help. That is kind of like you are capturing everything that you have seen in these 14 examples. But does that really mean like this 14 example explains the entire space of decisions? Like, is that a comprehensive set that you convince yourself like 14 is enough? Or like, do we even trust that this 14 covers all the possible cases for making a decision whether Alex is going to play tennis or not? Probably not. Okay, but then in the real world, the possibilities are infinite and you cannot iterate over them. So now it's a chicken and egg problem. You know this is not right, but you don't know how to do the right thing because you don't have all the possible data, all the possible outcomes. You have not observed it. This is a partially observed data set. And maybe something that you are learning from this data set is just a coincidence. It's not actually what matters in the real world. It's just so that this data set is so small, that thing just happened by chance. And you just happen to pick that up because your observation is so biased. So basically in the real world, probably it's not going to hold. Yes?
So is the solution to overfit just have a larger data set?
Good point. So if you think about this, if you had all the possible cases in your data set, then you will probably not have overfitting problems, right? Because you have seen all the cases. So definitely, yes. If you increase, the chances of overfitting goes down. But it also depends on the model, just not on the data, right? Because if you remember, if you take all your attributes and all the data in the world and just memorize everything, then you have again overfitted, right? Definitely, increasing your training set helps your model become more general, but that's just part of it, one part of the story. There are other parts. What happens to the data that you have not seen? Because in real life, you can never guarantee you have all the possible data. So the best way to do generalization, so overfitting is kind of counter part of generalization. Whether you are actually capturing the general knowledge or not, or are you just memorizing this data set? So overfitting is basically memorization, rather than truly capturing the knowledge. But it's hard to quantify because you don't have the real data. So the best you can do, what is the best we can do? We cannot have all the possible cases in our data. We cannot observe all the possible cases. It's just too expensive. Best guess. How do you know it's the best guess? You need some way to evaluate. Learn from every new data. But how do you know you are making some progress? Yes. But still you are optimizing on the training data that you have. I mean, every time you have the same problem, you have a larger amount of data, but that data is never enough. Yes. Assumptions. What?
Well, the problem with the existing data is that it's naturally a subset of the larger thing, and that's just how it is. That's just
Yeah.
the unfortunate reality. So then you come along as a smart human and try to grasp at some basic properties that connects this small subset to the larger population. That's where your assumptions come in.
Okay.
That's some ideas about the connection.
So you are assuming the real data, the training data kind of captures the properties of the real data. That's the assumption you are making. Yes. What?
Split the data set into like a training test and then see how it does afterwards on stuff that's not seen.
Excellent. So the other idea is you just split your data into training and testing. And then you just train on a partition. If the model you are training is general enough, if that is the true model, it should also hold for the testing data, which you have not for training, used for training. And then you can quantify that, right? You can quantify, okay, based on the testing set, this is what I see. And again, like if I have another model, that testing number goes up or goes down, so you can evaluate how much progress you are making. Right? So you want to have a quantification of learning. That, and what really quantifies learning is basically, if I haven't shown you an example before during training, something unseen example, that's what we call. The model has never seen, but makes the correct decision. That means it has learned the right knowledge. That's why it can classify or put a label on an unseen data correctly. Because you can always make a model, given that you can go to infinite complexity of the model to perfectly do the job on the training data. Because you know what is there, right? You should be able to capture all the possible cases and all that, but you never know whether that was a general knowledge that you actually captured that is something useful unless you test it out on unseen examples. Yes?
So is there a smart way to divide between training and testing? I know in the homework it was 1/3 versus 2/3 of your data set. Is there a smart way to do that, or is it just make a cut somewhere?
Good question. So the question is there a smart way to split the data set into training and testing? And there are many ways. For example, the first answer is there are many, many different ways to split that. But if I want to call a particular one smart, probably I don't have one that I will say like this is the smartest way, but there are definitely some dumb ways. Don't do that. Right? And we will show you how to split and all that. But I think a pretty solid baseline is just random partition. Just randomly partition your data set into 2/3, 1/3, 50, 50, 70, 30, yes. Yes, very good point. What if like my initial data set that I started with is already biased? So then it's just bad data. Right? It's just bad data. We cannot do anything about it other than collect more data. Okay? And that's why data and learning algorithm goes like side by side. And until you have both of them at a reasonable place, you cannot do good machine learning. And that's why neural networks failed for 20 years. And like people stopped doing neural networks. Because either the models were not complex enough to be run like with the hardware that were available, or we didn't have enough data to see in the 90s. Trust me, all the models you see today were proposed in 90s. It's just minor changes that are happening in this decade. The core ideas were there, but it didn't work. All right. So overfitting. So let's take an example, right? So this is the tree we have learned, but let's say we have another example, training example number 15, a noisy example. And what it means by noisy, maybe the label is actually wrong. In the data set, the label was no, but just assume that that's a wrong example that was included in the data set. In real life, you will not know that, but assume that we know this is a wrong example. But if we had this example in the tree, how would this tree, in this data set, how would the tree change? Can we still use this tree? Mm-hmm.
It's not going to play, but there was just some noise, and then we don't have a branch for overcast, so we need to another.
But this example is actually looking at sunny, right? And then you were already through this branch. And then for humidity, you have high or normal. But your decision tree is saying, if your humidity is normal, that's a yes. And what do you have in that example? No. So can you now stop there? No, you have to look at additional signals. But because that data was wrong, you are unnecessarily complicating your tree, just getting misguided by this single data point, which is a bad thing. Just in order to capture this one case, you have to make your model more complex. Maybe not a very good idea. So it's fine to capture most of your data with a simple model rather than having a very complex model capture every possible case, because there is always a possibility that your data is going to be noisy. So trying to build a very complex enough model to capture every single instance of your training data, which may not be actually true or which may not be actually necessary in the real world, is actually overfitting. You're just trying to overfit your training data, and in that process, the model has become so complex, and it doesn't hold true for the real life. Because if that example was actually yes, you could have stopped there. Maybe you will see future examples where this tree will not work on the testing data if you actually increase the tree. So it's always best to have a trade-off between simplicity and coverage. Okay? So properties, as I said, we want to have some kind of evaluation metric that quantifies what is my success, what is the accuracy, or what is the error rate of my model. Because most likely, it never happens that your model is 100% of the time correct. Then there is no point of machine learning. Question, yes?
So is ID3 the name of this 3D algorithm?
Yes.
Why is it called ID3?
I think it's induction tree. Like inductive decision tree algorithm, so that's why. But I can confirm that. Don't take my word for it. Okay? Sometimes things, after you work for a while in a particular area, then some things become so obvious, you stop thinking about why was that. But yeah, that's a good point. Most likely induction decision tree or something. Yeah. So we want a hypothesis or a tree that has the minimal error rate on the true data, on the true world. And the true, nobody knows what is true, because we are limited as humans. We have limited sensors. We don't have, like, if we think about something like a omnipotent kind of thing, we are not that. We don't know everything. So what is true is a philosophical question, and we cannot claim something to be absolutely true. Everything is based on our senses, we have sensors, right? We are subjective sensors. We are sensing this environment, and we are limited. So what is true, nobody knows, but our goal is to quantify that true error rate, which we cannot. So first, what we can do is to compute the error rate for our training data, but we have learned that we can do better. Just looking at training data is not a good idea. It might overfit. And you cannot go to the real data because you don't have it. So you need something in between, and then what you are assuming is your training data error is a lower bound for your true error. The true error will be higher, most likely, because you are observing partially. And that happens a lot of cases when we see in the training and testing partition, the amount of accuracy you have, or your error in the training data, for your testing data, that error goes up, because those are unseen examples. So it's like your training data error is like this, and maybe the true error lies somewhere here on the real data, but the testing will give you some better estimate of that. It may not be the right, but still it's better than only the training data. And that's why you split. And there are more ways to split, like validation, and I'll come to that later. But the whole point is you split your data set into training and testing. But it's kind of like, what is the problem with this kind of like just plain two partition splitting? Yes?
Well, you're losing some data to train on.
What?
You're losing some data.
You are losing some data to train on. Definitely. You could have used that data for training, but then your model could be better, but you never know, because you need some data for testing. Yes, what else? Yeah.
Depends on the data that you trained with, because you could either be getting the high regime of some data or the low regime, and you might not properly account for all your uniqueness of your data.
You mean we didn't partition it in a proper way? Okay, yes, maybe. So that blame probably goes to the partitioning algorithm. It doesn't go directly to the fact that we need to partition. Think about this. You're training on some model, you are testing on something, and you see that it's a very bad performance on the testing data. Can you do anything about it now? How? If you start over, the same partition is going to be very similar. Split it again. So you need some way to split multiple times and test it out. And that's why there is another partition that we want to create that is called a validation set. So what you do is first create, this is your entire data set, right? But in order to really test on unseen example, there has to be a test partition that the model has never seen. You cannot touch that until you are sure that this is the model you are going with. Because if you are looking at the testing set multiple times and just optimizing for that, that is also basically becoming part of your training process. You cannot do that. So you need to simulate, you have to have a simulated testing set before the actual testing set. So you partition it, testing, and the rest. And this part, you split between train and simulated test. And you can do different ways of partitioning here. You could randomize this process, do it many, many different times in many, many different ways, because all of this is basically your training data. You are just kind of creating a simulated or like virtual testing portion. And this is what is called a validation set. So now you can create many, many different partitions. Assume that one partition is training, the other partition is testing. And you look for all possible models that you can train. Not obviously all, because that will take forever, but whatever you can with your computational budget. Pick the best one that does the best on the simulated testing, and then call it like, okay, I'm ready. And hope that will do good on the real testing. Yes?
If you're splitting something once and then you split it again, right? What is this order of magnitude that we need to be working with in terms of like quantity of data?
That depends on your model. As I said, like in machine learning AI, at least in machine learning, whenever we talk about something, you cannot just go in one axis. Data is just one axis. If your model is very complex or like you need more data. If your model is simple, you probably don't need much data. If it's a decision tree, maybe some thousands are enough. If it's a complex transformer neural network, you need millions. It depends, like how much complexity your model has.
So there'll be some bias towards the simulated test data, is that right?
Your model will always have some bias, right? Because no model, remember, after you finish this course, you will not learn any single model that is right. That is very important to know. No model is right. Every model is wrong. Just some models are useful. And we are going to teach you ways to find out some useful models. All right? So here is an example, like a study that shows, like as you grow the size of the tree, what does that mean? Like the depth increases, right? And that is going to create some problems. What is that? As you make your tree more and more complex, what is supposed to happen? Yes. It is supposed to overfit, right? And can we see that from the data? Do you see that? Increase or decrease?
On test data.
That's a good question, right? So tell me more.
The training data
is increasing. So you are capturing more and more of the training. But what is happening on the testing? Decreasing, or it's like a plateau. It doesn't matter. So why complicate your model anymore? You're just now capturing unnecessary things here. Your model is still growing. Your computation will increase. It doesn't give you high accuracy on ANSI data. So the best way to figure out whether you are overfitting or not is to just keep adding complexity to your model and see whether you are still increasing the training accuracy, but your testing accuracy is not increasing or even dropping. So there has to be, based on this curve, tell me what is a good point to choose. What would you, as a company manager, let's say, running a machine learning model, which model you want to choose? 10? 15? Yeah? At the intersection, okay? Sure. I mean, you know, well, there is no right or wrong answer, but the point is you want to choose something here rather here. Right? Because you know for sure the further you go to the right, you are overfitting. So this is a key issue in machine learning, right? You can always add more data. You can always make your, or if you have more data, you can make your model more complex. That doesn't always help. And in any model that you learn, you need to find out the right balance. Are you overfitting? Are you underfitting? Or are you doing the right thing? And there is no single definition of right. This is where your experience will come as a machine learning engineer or a data scientist. Sometimes the accuracy is not very important. Precision is important. Sometimes the recall is important, and we'll talk about those metrics. This is just one metric we're looking at. And depending on your domain, you might have a different metric that you are trying to optimize. And then you again have to look into how complex your model is. Maybe your model is not overfitting or something, but it's still too large. It still takes so much time that, think about this. You search on Google, it takes a minute to give you the results. What happens? You just kick your monitor, right? Or like you destroy your computer. That doesn't help. So in real life, you have to optimize for efficiency as well. All right. Assignment 1 is out. It's due next Tuesday or Thursday, I forgot. It's written there. I mean, October 31st, I think. August 31st, sorry. No, don't do that. Don't quote me, like I want to be on record. No, I didn't say that. It's August 31st, okay? All right. So we have talked about this, learning theory, what does it mean to generalize, overfit, Occam's razor, simplest model. How do you choose a hypothesis space? That's what we initially told, right? That box we are trying to learn has infinite possibilities. We are making some assumptions there. And in this case, we made that is a decision tree. It has got like categorical variables and a lot. And you will see them like more, it will be more apparent to you once you see other models that we are going to start in the next class. It's hard to like just know the limitations and pros and cons just by looking into one model. We will talk about them. We will keep comparing with decision tree models later. Yeah, and we finished with like avoiding overfitting kind of thing. That's it. Questions? We don't have time to discuss projects today. We'll do that in the next class. All right, see you then. Good luck.